Okay, so it looks like everyone from the lobby is now in the room, so I'm going to go ahead and start. Um, just wanted to welcome everyone here. For those of you who don't know me, my name is Chris Glover, and I support the energy recovery restoration projects here at AirExchange. I'd like to thank you for taking time out of your day to join with us. Hopefully everyone can hear me and see the slides okay. Just for reference, there is a chat box that you can enter questions. I'll check that at the end, but feel free to enter them as they kind of pop in over the next 20 minutes or so. So we always have a pretty diverse crowd of people who join in on these conversations. So what I try to do is create a presentation that can speak to everyone in the audience. So hopefully everyone has an opportunity to learn a little bit. As always, if you do have specific questions, you can ask them at the end, or feel free to reach out to me by phone or email as well. Okay, so there is a little bit of latency based upon how many people are in the room right now. So it is going to take a second for some of these slides to load up for some of you. That's normal. But on the agenda today, we're going to talk a little bit about the ERV winter operation. We will have a discussion on psychometrics. Don't get all nervous. Not everyone has to be a psychometric expert to understand what I'm going to talk about. And we're going to end up the discussion with strategies for frost control. And I'd like to say that frost control routinely is one of the most discussed topics when it comes to energy recovery. And I like it because it's one of those items that is really specifically revolves around the ERV operation. Okay, so energy recovery is used in the wintertime to recycle the heat and humidity that's contained in the exhaust air, and it's using that heat and humidity to heat and humidify the incoming ventilation air. So looking at a typical system, the outside air comes into the unit and is heated by the primary heating element to a temperature that's suitable to be delivered to the space. And that heated air then dilutes the space air with fresh air, and the stale air is then exhausted back out through the unit. Now, at this point in the operational process, the exhaust air is typically warm and has picked up a bit of humidity. Now let's look at that process, but adding an energy recovery component into the system. So instead of the primary heating element having to treat the entire ventilation load, the energy in the exhausted air performs a large portion of the work, which reduces the capacity required by the primary heating element. If you've ever chimed into one of my previous discussions, I often refer to this process as a load shift, where you are shifting the heating load of the primary heating element over to the wheel, which accomplishes the conditioning and the ventilation to the space. Okay, so pulling that wheel out of the system, let's take a closer look at that process. So you have the outside air coming in at 20 degrees, and you have the exhaust air leaving at 75 degrees. A percentage of that work is used to warm the incoming air to 63 degrees, as being demonstrated. And since the heat was exchanged to the ventilation air, it means that the leaving exhaust air is now going to be cooler as a result. So what does it really take to generate frost on an energy recovery component? Well, you really need two things. First, you need the temperature to be below freezing. If you look at the temperatures to the left of that diagram, you can really see that they're at or below freezing. And secondly, you need a source of liquid water. Now, one of these really isn't available during most normal operating conditions in the wintertime, and that's liquid water. And the reason for that is because the water transfer in an energy recovery process is transferred by the method of adsorption. Now, one of the most common misconceptions is that it's the outside air temperature that drives the frosting process. And while it's true that you can't freeze water if the temperature is above freezing, the most important element in determining whether frost is going to occur is the indoor humidity. And the next couple of slides, I'm going to try to demonstrate why. Okay, so we're going to discuss a bit of theory regarding the frosting process. So for the next couple of slides, I'm going to use a psychometric chart to kind of visually demonstrate the ERV winter operation. Now, I'm not expecting everyone here to be an expert on psychometrics, so if you've never seen one of these or haven't seen one in a while, don't worry, I'm going to explain a few key items. But I like to use this as a visual tool because I think it does a really good job of explaining what is actually happening in the system. So first, the horizontal axis represents temperature. The very cold temperatures start on the left, and as it moves over to the right, it gets warmer. The vertical axis represents humidity, starting with very low absolute humidity on the bottom, and as the condition gets more humid, it moves to the top. The curved lines in the middle represent relative humidity. Relative humidity is a measurement of how much humidity is in the air compared to how much there could be, starting at 0%, which is completely dry, to 100%, which is completely saturated. The top curve line represents when the air is completely saturated, meaning the air cannot hold any more water. I'm going to refer to this as the saturation line. So this is when the air has reached 100% relative humidity. So now, in regards to the frosting point, this is probably the most important line to pay attention to. So what typically happens when air reaches 100% relative humidity? Well, if you're outdoors, it could start to rain, but it's when the vapor in the air could physically condense. So please keep that in mind as I go over the next couple of slides. Okay, so borrowing from our previous slide, let's plot this process on the chart. Our outside air is 20 degrees, and our exhaust air is 75 degrees. Now, if we draw a line between these 2 points, this represents the ERV process line. So anywhere on this line is where the leaving supply and exhaust air will end up. And we can also take note of this line, which point has the most humidity? Well, in this particular case, it's the exhaust air that contains the most humidity because it's higher up in the chart. So looking at the diagram in the upper left, this particular process has resulted in 2 leaving conditions. So the leaving supply air is 63 degrees and the leaving exhaust air is 32 degrees. So if you remember from a previous slide when I said you needed liquid water to form frost, in order to condense water on the heat exchanger, these points have to become fully saturated. So looking at this particular process, all the humidity has been exchanged in the vapor state. So neither stream has approached the saturation curve. So energy recovery is kind of unique in this regard because as the exhaust air gets cooled, it also gets dried, which means the leaving air naturally wants to move away from the saturation curve. This is really the unique process that what drives or minimizes the risk for frost in an energy recovery device, even in colder environments. So keep in mind, once again, in order for the water vapor to condense, that process line has to come in contact with the saturation line. So now let's take a look at that same example, but let's lower the outside air temperature to 0 degrees. And let's plot the new leaving supply air and the new leaving exhaust air. You can see that the process line has come closer to the saturation line, but it still hasn't intersected. So theoretically, even in this process, which is really, really cold, you're still not physically condensing water vapor on the surface of the wheel. So you're still not condensing frost, even in this relatively cold environment. And the reason that I'm kind of walking you through this and showing you this is that because I really wanted to demonstrate that the outside air temperature usually isn't the biggest determining factor when frost forms. So let's take a look at one more condition, but let's keep the outside air the same, and we'll raise the humidity of the exhaust air. So let's plot the supply air condition, and let's plot the exhaust air condition. So now, what's different about this process versus the previous one that we looked at? Well, this process line has now come in contact with the saturation line. So what did it really take to accomplish that? Well, in this particular case, we had to raise the humidity quite a bit. So if you remember a few slides ago when I pointed out the humidity levels, it's because I wanted to demonstrate that how much of an impact the indoor humidity makes when determining if there's a frosting condition. One thing that I like to point out as somewhat of a rule of thumb is that for most commercial spaces, they have a tendency to dry out during the winter months. So in a practical sense, while the design may have a high relative humidity, the actual operating conditions are usually quite less than that. So now that we have a process that could result in frost, what are the popular methods to allow a device to work in these conditions? So I have four different methods. These are very common control strategies in the market, two of which you can use on both wheels and plates, and then all four you can use on wheels. So the ones that you can use on plates as you're paying attention are going to be preheat and bypass, but all four of them can be used on a wheel. So the first method and that I'm going to discuss is preheat, and it's really the only method that allows you to use the full potential of the wheel of the device. I'd also like to point out that regardless of how you're going to control frost, one of the easiest ways to accomplish in determining whether you're going to have a frosting situation is to use the AirExchange web-based software, AirExWeb. You can access it at www.airexweb.com. Once you open up the software, you're prompted to create a new project. And as a part of that process, you enter your operating conditions in your location, and it's going to calculate whether or not that particular condition is going to result in frost. So this way, you can bypass the need for opening up a site chart in general, and you can just use the software to determine it. So those are the conditions that you would enter in that particular case. Okay, so starting with our frosting process, let's take a look at the preheat option. So please keep in mind that preheat is the only method that I'm going to discuss that allows the user to get the full performance of the wheel during a frosting condition. And being a design point reduction tool, on those very cold days, you really, really want to get the most performance out of these devices because they're really minimizing how much energy you have to use in your primary heating element. So what preheat does is you add a preheater to the system, and while yes, the purpose of this preheater is to warm the air, the true benefit that you're getting of this heater is that it's lowering the incoming relative humidity of the air. So you're changing the slope of that process line. And that's one of the real reasons that you don't have to heat the air to 32 degrees to mitigate frost. So in this particular case, we're only heating the air to 10 degrees coming off that heat exchanger in order to stop frost from forming. So plotting that process really demonstrates what is exactly happening in the system. So starting at 0 degrees, the air goes through the heater and is warmed to 10 degrees. You can actually see the slide chart move over there. So this warms the air and it lowers the relative humidity, which changes the slope of the process line enough so that all the operating points are no longer becoming saturated and all the moisture exchanges happening once again in the vapor state. And as you can see, all it takes is small amounts of temperature rise can have a substantial impact on the changing of this particular slope. And what this does, it allows you to get the full performance, the full effectiveness out of the device. I also like to point out that while most cases the preheat is added on the outdoor air side where it's warming the incoming air, but preheat can also be added on the exhaust air side. So you'll plot these particular points on the process side here. you'll see that you physically have to add more of you have to have a greater temperature rise. So in this particular case, it's a 25-degree rise versus a 10-degree rise on the outdoor air side. But what I'd like to point out in this particular configuration is that the energy that you add into the system is recoverable. So this means that the heat can be used to raise the leaving air condition. So now we're coming off the wheel at 75 degrees versus 58 degrees before. So now that we understand some of the theory behind the preheat process, let's talk about some of the practical applications and integrated control schemes. So one of the things that I'd like to point out that these are just suggestions. This is not gospel. There are many ways to do this. There's very easy and inexpensive ways to very expensive and more elegant ways to do it. But these are the ways I like to point it out, and really you can make the determination on which the best way to control it is based upon your particular building. So first and foremost, you would determine whether you have frost using the AirExchangecom software. So we did that before, and it determined that we did. So the easiest way and probably the most inexpensive way to control using a preheater is to use a dry bulb sensor on the outdoor air side. You would use the software to determine what your control temperature is going to be, and then you would modulate that preheater based upon the incoming air temperature to modulate the heat. Now, as a rule of thumb, if the temperature is below the frost threshold, you'd want to turn the temperature on to maintain the desired inlet temperature. You can get a little bit more elegant by doing a comparative analysis using your exhaust air temperature, and this will help minimize the operating hours where you're frosting, where you're not actually having a frosting condition. So as a rule of thumb, the preheater frost control works best for applications that really have a moderate to high indoor relative humidity or extremely low air temperatures. So I know examples of these spaces would be buildings that have mechanical humidification, pools, yoga studios, etc. Also, if you're designing a building that's in an area where you have a considerable amount of heating hours, one thing to take into consideration is that preheat is the only method that allows you to take full advantage of the component's performance. And if you're in a predominantly heating environment, those are the days you typically need the most out of it. Another an easy and inexpensive way to get the most out of these devices, and personally what I find works the best, is to use a relative humidity sensor on the exhaust air side. This is probably one of the cheapest, easiest ways to maintain that you're not turning this preheater on during conditions where you're probably not having frost. So what the relative humidity sensor is going to do is it's going to look at the exhaust air and whether it's becoming saturated. So as the relative humidity on the exhaust air starts to get higher, what you would do is you would modulate the heater to lower the incoming relative humidity. And that's done through a very kind of simple loop PID process, which is fairly inexpensive these days. Okay, so the next method we're going to discuss is wheel speed control. So with wheel speed control, the premise is to slow the wheel down to warm the core temperature of the component. So by slowing the wheel down, what you're essentially doing is you're spoiling the wheel performance and you're minimizing the wheel's ability to transfer heat and humidity, which subsequently warms up the core. So let's plot this process on the chart. And as the wheel starts to slow down, the leaving conditions gradually get closer to the entering conditions. So the exhaust air gets warmer and the supply air gets colder. So slowing the wheel down has moved these two state points away from the saturation curve. So one of the things you may have noticed is that during that process, the points didn't move up and down the standard process line. And that's because as you slow the wheel down, it becomes more sensible in nature. The latent curve and the thermal curve are independent of one another. So looking at the resulting process in the left-hand side of the screen, you'll notice that you're not getting as much work out of the wheel. So you have to take that into consideration when you're designing your system. So what would have been a 56 discharge temperature is now at 22 degrees, which means that your primary heating element has to take that into consideration on these really very cold days. So integrating wheel speed control into a system, once again, use the software to determine if you have a frosting condition based on the operating conditions. And if you do, there are really two common ways to set up the system for wheel speed control. The first is a series of dry bulb sensors, one located in the incoming outside air to monitor whether the temperature is below frosting, and the other would be located in the leaving exhaust air to modulate the wheel speed to achieve a desired leaving air temperature. So you would determine this and what temperatures to use by using a manufacturer-provided chart like the one on the left. This is something that you can download off our website or in our product catalog. The second way to accomplish this, and I spoke briefly about this on the previous slide, is to use a dry bulb sensor and a relative humidity sensor. So once again, you would place the dry bulb sensor in the outdoor airstream to monitor if the temperature is below the frosting threshold. And the humidity sensor would be placed in the leaving exhaust air. But instead of modulating wheel speed to achieve a certain temperature, in this case, you're modulating the wheel speed to achieve a certain relative humidity. So what I find that most people do, and in most cases, is they like to keep the leaving relative humidity below 90%. So as a rule of thumb, by doing that, wheel speed control is best suited for lower humidity spaces and more moderately cold environments. So these are the spaces that typically don't have very many hours where this type of operation is going to occur. Typical spaces would be K through 12 classrooms, office spaces, and retail environments that typically don't operate 24 hours a day, and they're not subject to the very, very cold temperatures overnight, as well as very high indoor relative humidities. Okay, our third method is airflow bypass, and it kind of works on a similar principle as wheel speed, where you're trying to minimize the wheel's ability to transfer heat and humidity. So what you're doing is you're bypassing a portion of the air around the wheel, and what you're essentially doing is you're minimizing the pool of energy that you use to condition the air. Unlike wheel speed control, which follows that really odd performance path that we saw before, when using bypass dampers, the operating points do follow the typical process line. So as you start to bypass the air on the leaving on the supply side, the exhaust air starts to warm, and conversely, so does the leaving air condition. So you can see that it slides those points up the line. So by doing this may appear to be a kind of a win-win situation where you stop the frost from forming and achieved higher leaving air temperatures. But the thing to keep in mind for this particular process is that you've also bypassed a portion of the air at that lower temperature, which is now creating an overall lower entering air temperature to the primary heater. So once again, always check to see whether you have a frosting, point using the software. So for using a set of dampers, what you can do is, once again, use either a set of dry bulb sensors or a dry bulb and a relative humidity sensor, and you essentially follow the same steps. So in both systems, you use the dry bulb sensor to monitor whether the outside air temperature is below the frosting threshold. And you would use the subsequent sensor on the exhaust air side to modulate the damper to achieve either a desired leaving air temperature or a desired relative humidity. I also like to point out that for these particular systems, because bypassing the air follows a more traditional performance path, it often can be used pretty reliably, more reliably than wheel speed control as an indoor relative humidity starts to rise. Therefore, as a rule of thumb, bypass can be used in what I consider a little more moderate applications to low humidity applications. So typical spaces would be universities, schools, research buildings, gymnasiums. So these are the buildings that are starting to get greater operating hours and also have the ability to have more or have higher indoor relative humidities than you typically associate with some other buildings. And the last method that I'm going to discuss very briefly is the Stop Jog method. This was very popular, maybe 10, 15 years ago. It's become less popular over time because VFDs have become quite inexpensive, and it's really supplemented that process. But it's a really simple process, and it works. So the Stop Jog method typically uses a single dry bulb sensor to determine if you're below the frosting threshold. And once the air is below that frost threshold, the system simply just starts and stops. And this intermittent process really keeps the frost from forming. And it'll do this until the process or the outside air temperature is above the frosting threshold. So this method allows you to get what I'm going to call slugs of performance. So when the wheel's spinning, you're going to get a little performance out of it, but zero performance when the wheel's sitting idle. So because of this very unique operational pattern, the nature to this method, it is usually used in buildings that have a very minimal amount of hours that could be subject to a frosting situation. But it's very inexpensive and it works. So I would say that as a rule of thumb, So as a rule of thumb, I would say Stop Jog is best suited for applications that have low chance of frosting occurring, and where the humidity range is fairly minimal. The opportunity or the building's ability to maintain a high humidity in the winter is very, very minimal. Okay, so that was quite a bit of information, and I never expect anyone to remember everything. So where can you go to find more? I'd first start off on a website, which is AirExchangecom. We just recently updated it. So please feel free to plug in and give us your comments. We'd love to hear about it. Here you'll find access to all our technical materials, case studies, relative industry information, contact information, as well as links to all the software that we discussed during the presentation. You'll also be able to find a parts and replacement wheel section on there for those that are really in charge of servicing and maintaining wheels. So please feel free to stop by and take a peek at it. There really is quite a bit of information that's available to you 24/7. We also have our web-based software, which is at www.airexweb.com. What I really like about this is it keeps everything in the cloud. Now, I don't particularly like that term, but what it allows us to do is all our wheel configurations are updated in real time. So no matter when you access this, you can be ensured that you're using the most up-to-date and accurate information that's available to us. It also allows you to save it remotely as well as share with others in your office. So I hope you get a chance to use it. I'd love to hear about comments, or if you have any questions about it, feel free to reach out to us in the meantime. And lastly, if you need to get a hold of me, here's my contact information. Feel free to reach out with comments. We will be posting this this presentation online for those who weren't able to make it. Also, reach out to me. I'd like to hear about things that you're seeing in the marketplace, questions that you may have, or any ideas that you have for future presentations, things that you believe would be beneficial to you. Please feel free to reach out to us and discuss those items. So. With that being said, I'm going to go open up the chat box. But once again, I really appreciate you all taking the time out of your day. And I hope you got a little bit out of this particular webinar. So thank you very much. Okay, so Rich asked if we can get the slides. Absolutely. Just for those of you who want to get a copy of the slides, it's kind of a big presentation. So what I'll most likely have to do is create a Google Drive for it. So reach out to me after the webinar, and I'll put it in a drive and just send you a link so you can download it when you're ready. Okay, so what is the purpose of the jog for stop jog control? And it's really not to really get any particular performance out of the wheel. It's really there just to mitigate frost so that doesn't cause any type of material damage to the wheel itself. So of the four strategies that I spoke with, the first three really allow you to get some performance out of the wheel. The stop jog is really there just to kind of keep the frost from forming, but you're not getting any real benefit of the wheel in that particular case. That's why I recommend using it only in those applications where you're really subject to a very minimal amount of operating hours where a frost threshold might be there, or if you know that your indoor humidity is going to be really dry during those winter months. Question was about jog. So when I mean stop jog, I guess the best way to describe it is it's a start and stop cycle. So the wheel typically operates for a minute, stops for a minute, operates for a minute, stops for a minute. That's what the jog is referring to. So, and it's really there just to keep, if frost does have a chance to form, it's just there to uh, we rotate against us to melt it and re-evaporate it in the airstream. What type of damage can occur due to frost? So, I mean, personally, frosting is one of those things that I think everyone's worried about it. But I'll be honest with you, I've been working for the company for about 14 years now. I've had problems with frost on probably 10 applications of the tens of thousands of wheels that we actually send out there. And it's usually on applications that have exceptionally high indoor humidity. So if frost were to form on a wheel, theoretically, what's going to happen is it's going to start to block airflow. And the blockage of the airflow typically leads to stress on the media as well as any of the other components within the structural nature of the device. And in those particular cases, depending upon how much stress, you could get some mechanical failure. I will say that that is highly, highly unlikely. And even in the applications where I knew frost was forming, and I hate to pick on them, but one of the trickiest applications these days are those indoor hot yoga studios where they like to keep the air at about 100 degrees and about 9,000% relative humidity. Those are really the types of situations where it's going to form enough frost to physically damage the wheel. But theoretically, if you let it frost up enough, it would create a barrier, the pressure drop would increase, and then you could possibly, have some mechanical failure, but it's very, very unlikely that that's going to occur. Okay, scrolling down here. Hold on a second. It just takes me a second to kind of scroll here. How high indoor? So that was kind of, I kind of spoke about that in the first couple of slides. So let me try to back this up a little bit. In most cases in North America, so as a rule of thumb, if you're below 30% relative humidity indoors in the wintertime and you're at or above 0 degrees Fahrenheit, as a rule of thumb, I like to say that you're probably not going to have frost from forming. So as you start to work on these applications where you're finding that your exhaust air, or excuse me, that your outside air temperature is dropping below that, or if you feel positively that the indoor humidity in the wintertime is going to be above that, those are the types of situations that you want to pay more attention to in terms of looking at your operating hours and your bin hours to see what exactly is happening in the system. Not suggesting you take a psych chart out for all those. Once again, you can physically just go to our software and plug in those conditions, and it's going to calculate whether there's a frosting condition on those particular conditions or not. But typically, as a rule of thumb, the humidity, it takes smaller amounts of humidity increase to raise the frost threshold than it does temperature rise, than negative temperature. So it's really the humidity is the indoor humidity is the biggest culprit in determining a relatively high frosting threshold. I have seen, so the next one is, have you seen a frost control initiated by pressure switch? And I have seen that. The only thing with that is that sometimes it can give you a false negative. And the false negative is not necessarily frost from forming, but the wheel starting to get dirty over time and not being maintained properly. And as we know, a lot of these devices that go on the market don't always have the best preventative maintenance, and you don't want the frosting control cycle starting to happen on those particular cases where you're not having frost, but it's just the wheel being dirty. So it has to be a little bit more elegant than just a pressure switch. So you have to combine it in terms of temperature or operating schedule in order to determine whether it's frost or the wheel getting fouled up and it needs to be maintained. Okay, so where can I get? Okay, so after the presentation, what I do is I sent out a link to everyone to give them access to the webinar. So it usually takes about a day or everything to appropriate, because we put it on YouTube. So, but everything should be available by the end of tomorrow at the latest. Okay, so is frost worse for polymer or aluminum wheel material? And it's exactly the same, because it's not necessarily the wheel material that determines frost, it's the process that determines frost. So regardless, and we offer both types of media, to be honest with you. So you'd use the same exact methods to determine whether frost is forming, whether using one of our polymer wheels or one of our aluminum wheels. And actually, for that same thing, if you go onto our website, you can actually just plug in whether you want polymer or aluminum and the design conditions, and you'll see that they're exactly the same as well. So I try to answer everyone's questions based upon the text. Now, some things do get lost in interpretation sometimes. So if I didn't quite answer your question, or if I didn't explain it properly, once again, please feel free to reach out to me. That's what we're here for. Otherwise, if you had something that you didn't feel like asking during this time, email to me and I'll get you an answer after that. But at this point, are there any other questions out there? So it doesn't look like it. So once again, thank you all for being here. And hopefully you guys can chime in on our next webinar, which should happen in about a month or two. So keep an eye out for that notification. Thanks again. Take care, everyone.